All right, let's talk about graph theory. We'll start with the basics, definitions, things. So let's start here. So I've got a picture of a graph. We're going to go through these definitions, and I'll kind of pick out what we've got. So a graph is a set of finite vertices and edges that start and end at vertices. So there's our graph. So a vertex is a point or dot of a graph that is often labeled as a capital letter. So it's usually labeled like a capital letter. Sometimes the homework will use words, like sometimes these vertices represent cities, so they'll write out the city name. All right, so let me start labeling what we've got. All right, so these letters, these are vertices. So this is a vertex. Any of these letters are vertices, even this one that has this weird circle with it. But what I do want to mention is that this is not a vertex. So just because lines intersect doesn't make it a vertex. Then we come to edges. Edges are the line segment or curves of a graph. So this is an edge. Turns out this circle thing is also an edge. It has this very particular name. So I'll label that next. An edge that starts and ends at the same vertex is called a loop. So we'll call it a loop, but it is an edge as well. All right. So let's do some observation of this graph. So this graph has 4 vertices, and they are, all right, A, B, C, D. So when we label these in the homework, it's customary to use a comma to separate. So the next one says it has blank edges, and those edges are what? All right, let's count them up. 1, 2, 3, 4. Turns out this loop is a 5th one. So it has 5 edges, and those edges are what we're going to do. I'll go ahead and write them out, and I got some notes about the edges. So each of these line segments or curves are edges, and I'll use a comma to separate them. So AD, AC, DB, or BD, either way. So we've got 3 of them. Let's see, did we do BC, BC? And then, of course, the loop is CC. So I'll go ahead and just note that this loop, that's the kind of weird thing we'll come in touch with, are these loops. So we can write any edge, AB, as BA. So just because I wrote AD, if you were thinking DA, that's fine. You don't put commas between the vertices, but you do put comma between the edges. So edges can be lines, curves, or loops. All right, so the bulk of this section is just a bunch of definitions. And we're going to go through them. So our first one, equivalent graphs. So if we've got 2 graphs, they're equivalent if they have the same vertices and they are labeled the same way. All right, let me show you what I'm talking about. So I'm going to draw these separate. I'm going to first start off with a graph that I found. I'm going to draw this out for you. Okay, these guys are connected like this. So this is W, this is X, Y, V, and Z. There's a little triangle right here. So I'm using basically straight lines. You can use some curves. In fact, I'll give that one a little curve. Doesn't matter. All right, so there's a graph, perfectly fine graph. So now I'm going to give you an equivalent graph to that. All right, so we got 1, 2, 3, 4, 5 vertices. I'm going to put these vertices in a row. Let's see. I guess I'll put our last one right there. Okay, so here I'm going to just label these V, W, X, Y, Z. I've chosen to put these vertices in a row to kind of illustrate a point that it doesn't matter the location of the edges. What matters is how they are connected. So I'm going to come up with a connected graph or an equivalent graph to this based on where I've put my vertices. So I'm going to go alphabetical. W. Okay. So W is connected to X. W is connected to Y. Uh-oh, how do I get there? Well, I could just do this. Or you could go anywhere, it doesn't matter. So, W is connected to X, W is connected to Y, that's it. Let me go to X. X is connected to W, we know that. X is connected to Y. And that's it. X is connected to W, X is connected to Y. Now I'll move on to Y. Y is connected to X and W and V. Oh, how do we get there? Well, I guess I've got to do this. I'm choosing to kind of do this rainbow look. You could go underneath. It doesn't matter. And then lastly, so Y is connected to W, X, V, and then V is only connected to Z. And that's it. So these two graphs are equivalent. The placement of the vertices does not matter. It is arbitrary. You just got to make sure that they're connected in the same way. All right, that brings us up to some more definitions. The degree of a vertex is the number of edges at the vertex. So we're going to do an example of that. I'm going to give you a different graph. Pretty straightforward. A vertex with an odd number of edges is an odd vertex, and a vertex with an even number of edges attached to it is an even vertex. And two vertices in a graph are said to be adjacent if there is at least one edge connecting them. So think of adjacent vertices as connected. So up here, X is adjacent to Y and W. W is adjacent to Y and X. Z is only adjacent to V, even though in my picture it's next to Y, because it's only got an edge that connects to V, means those are adjacent. But I'm going to give you a very specific example, so let me draw that out. We're going to introduce another loop, so here we go. All right, so let me go ahead and label where my vertices are. Start with that. Okay, I got an F there, an E there, G, C, B, A. Always use a magic marker to kind of make these vertices larger. All right, so F, E, D, C, B, A, R. Those are my vertices. The question says, which vertices are adjacent to A? Okay, Well, the only vertices adjacent to A are B and C. Those are the only ones that are connected. Now, the next question, what's the degree of each vertex? I think I'm going to answer this one up here. I'm going to give you a table. That's what you're going to see in the homework anyway. So what they do is they say, here's our vertex. They're going to label all your vertices. I'll do it alphabetical. A, B, C, D, E, F, and that's it. Okay. And then they want the degree. And I'm going to put whether it's even or odd. I know it doesn't ask for that, but just to remind us. Okay, so even / odd. All right. So A, the way this works is we got two edges that touch A, so the degree of A is 2. Of course, that is even. Didn't give myself much space here. B is also 2. Of course, that's an even number. C, 1, 2. All right, nothing exciting yet. D is 1, 2. Okay. Oh, C is not 2. C is 3. So that is odd. I knew something was wrong. I was like, they can't all be even. All right. What's next here? D is 2, which is even. E, I'm coming back to E because of that. F is 1, which is odd. All right. So E is the weird case because it's got these edges and it's got the loop. Turns out that loops are 2. And I'll write that down. So 1, 2, 3, 4, which is still even. All right, so note loops count as 2 degrees. So 1, 2, 3, 4. It's all about the number of edges that enter the vertex. Okay, so that's 1, 2, 3, 4. Whereas A was just 1, 2. It's a little tricky, but there you go. All right, now we can move on to paths and circuits. These are going to be very important in 14.2 and 14.3. So a path in a graph is a sequence of adjacent vertices and the edges connecting them. Although a vertex can appear on the path more than once, an edge can only be part of a path once. A circuit is a path that begins and ends at the same vertex. So what I'm going to do is I'm going to draw you another graph, and we're going to find a path and a circuit. Okay, actually, I think I'm going to give you a couple of examples of each. Here we go. So I'm drawing this out. I'll label my vertices in just a moment. This one is a little unique. It kind of has these end points. You can kind of see it ends here, or it ends down here, or it ends there. So the vertices are C, D, B, A, E, F, G. C, D, F, G, E, B, A. All right. The question says, find a path from B to G. Since I don't have a lot of space down here, I'm going to do that up here. So path from B to G. Okay. And there's a few. So I'll give you solutions. Solutions. You're only required to give one unless it says, which of these are paths. Generally, if you have to write it out, you only have to do one. So a path from B to G. Here's B. All right, I'm going to kind of circle that guy, and here's G. So any path I can take to get there is fine. When I say path, well, we start at B, I can go to D, and then F, and then G, B, D, F, G. Well, some of you probably noticed I could have also gone, instead of going to D, I could have gone to E. So B, E, F, G. But why can't I go B, D, E, F, G? I could do that. B, D, E, F, G. B, D, E, F, G. I could have also done B, E, D, F, G. These are all perfectly fine. I think that's about it. Why? Because if I try to go to A, I have to cross back over B. That's not allowed. I go to E, I can't go back. I could go here to D. I can't go back. F, G. And really, once I get to F, I have to go straight to G. So that's that. Those are all the paths from B to G I can think of. Now for the next part. It wants a circuit beginning with E. Find a circuit beginning with E. All right. E. A circuit means that I'm going to start and end at E. So I could go around the triangle. E, B, D, E. E, B, D, E. I could do this triangle. Oh, before I do that, I could go the other way. I went E, B, D, E. I could have done E, D, B, E. And go around this triangle as well. E, F, D, E, E, F, D, E. I could have gone E, D, F, E, D, F, E. I could also have gone around the large diamond here. E, B, D, F, E, and I could have gone the opposite way. E, F, D, B, E. E, F, D, B, E. That's about it. Because if I stray from that, if I try to go to one of these endpoints, which that's not really what they're called, I'm calling them that. If I try to go to A, I can't get back to B. If I try to go to C, I can't get back to D. If I try to go to G, I can't get back to F. So I think that's about it. But those are all circuits. Like I said, you're only expected to do one of those. Generally, unless it says which of these are circuits. All right. And my last page. We have connected graphs and disconnected graphs. So what I have for you, I want to make a table. I'll do that very fast. Let's see. I got a straight edge with me. All right, so in my table, I've got a connected graph, and I've got it split up so that you don't confuse whenever something is disconnected. All right, so I'll have my connected graph. And over here, I'll have my disconnected graphs. Well, I guess I should tell you what it means for something to be connected or disconnected. But I really wanted to show you my table and that I'm going to have some distinction. So a graph is connected if for any two of the vertices there's at least one path connecting them. Basically, a graph is connected if it's one piece. A graph is disconnected if it's not connected. They do that a lot in math, where they use the opposite. If it's the opposite of something, they will say, "This is the opposite." The one definition I'm thinking of in set theory is a set is, like they'll say a set is open if it's not closed, or it's closed if it's not open. That was one of the definitions. Anyway, all right. So let me draw you the connected graph. It's actually going to look familiar because it's the same one we did earlier. I realize if we can reuse some of these graphs, that might be helpful to kind of remember or realize not everything has to be different. So. Okay, let me put my vertices here. F, C, E, D, C, A, B. Okay, so that is a connected graph. I could get from F to A. I can get from F to C. I can get from C to E. These are disconnected graphs. So basically what I'm going to do is take this graph and break it into some strategic places. So here I'm removing this DC. So let me label my vertices. So that's FED. And then that's CAB. This is disconnected because we're missing one of those lines, one of those edges. And then another example of a disconnected graph I always like to demonstrate in class because it shows up in the homework is something like this. There's a loop, right? And it doesn't matter that the links are different. Remember, so that is E, D, C, A, B. And then we still had F floating around. So notice I took away EF. Technically, or not technically, that vertex F is part of the graph. So if I remove EF and you have a vertex floating in space, it's still disconnected. So that leads us to the definition of a bridge. A bridge is an edge that if you remove it from a connected graph, it leaves behind a disconnected graph. Obviously, the edges in this example, bridges in this example are DC. We removed DC. We removed EF. And it says, are there any more bridges? So what do you think? Are there any other bridges here? I think so, maybe. So EF we already talked about. If I remove EE, it's still connected. ED, did I do that one? I hadn't done that one. ED or DE. DC. And then, of course, if I remove AC, it's still one piece. I still can get from A to F. Or if I remove BA or BC. So this these are our only bridges. Okay, I believe that's everything we need to know. Basically, lots of definitions, lots of little facts, but we got to have a secure, strong understanding of this before we move into the next section.